Hello everyone, I'm Umayma Amdi, master student from ETS Montreal, and I would like to present to you our recent work entitled An Empirical Study on the Impact of Refactoring on Quality Metrics in Android Applications. Okay, let's get started. So today, Android has been the dominating operating system developed by Google for mobile apps, and Android is currently experiencing a huge expansion of its user base over the past few years. In 2020, there are over 3 million of Android apps that are available on Google Play Store, with over 1,000 apps published every day, and 1.5 billion apps downloaded every month. Google says that in 2020 there are more than 2.5 billion Android devices worldwide. And now users care more about the quality of their apps. They always want to have new features, they always want to have bugs fixed quickly, their mobile apps updated to new environment changes. Indeed, their expectations are very high. So here, the real challenge for Android developers is to satisfy user needs in terms of quality. However, maintaining high level of code quality is difficult in the context of mobile apps, since they have to evolve quickly to meet new user needs and technological changes. And addressing these constraints may lead to poor implementation and design choices that may degrade the quality. Indeed, many methods have been applied to improve software quality. Refactoring is one of those methods, which is defined as any change in the code that improves its internal structure without affecting its external behavior. It's a way to clean up code that minimizes the chances of introducing bugs. For example, move method, extract method, move attribute, move class. And developers refactor their code to address some quality issues that can be related to internal quality attributes, such as coupling cohesion, external quality attributes, such as readability, adaptability, and code smells, such as complex class, lazy class. Note that in our study we'll focus on internal quality attributes. There are several studies for over 20 years that focused on some specific quality attributes such as cohesion, complexity, and their relationship with refactoring. All these works focused on desktop applications, but we are not sure whether the same findings applies on mobile apps, which motivate us to explore current practice on mobile apps. This gives rise to our goal and research question. The goal being about how refactoring affects structural quality metrics in Android apps, and in particular address the following research question. Do refactoring applied by developers improve quality metrics? To do so, we designed a controlled experiment where we select two groups of code changes. A first group that consists of refactoring related changes, the treatment group, and a second group that consists of non-refactoring code changes, the control group. Thereafter, we investigate the impact of both the groups on quality metrics to allow statistical analysis. So as you can see, the process comprises a sequence of 6 main steps. In the first step, we select the apps. We target open source Android apps that are freely distributed in Google Play Store and have their versioning history hosted on GitHub. For this purpose, we performed a custom search on GitHub by targeting all Java repositories in which the README file contains a link to a Google Play Store page. Overall, we obtained 1900 2012 apps. Then, we applied the following filters to exclude apps whose GitHub repository does not contain an Android manifest file, as they clearly do not refer to real Android apps. Then we exclude apps for which the corresponding Google Play Store is not existing anymore. And finally, we exclude repositories that contain forks of other repositories. In total, we obtain 1,923 apps. Then, we randomly selected 300 apps. In the second step, we collect all the refactoring applied to the studied apps. Then we collect the commit changes before and after refactorings. Next, we extract a set of commits that contain non-refactoring changes of our controlled experiment. To do this, based on the treatment group, we randomly selected a set of non-refactoring commits representing our control groups. And then to assess the impact of refactoring on software quality, we measure a set of quality metrics for each applied refactoring change as well as non-refactoring change. Finally, we investigate whether or not each metric is improving by refactoring using statistical methods. So to detect refactoring, we use the refactoring miner, which is a command line based open source tool. The tool works through the commit history of a project's Git repository to extract refactorings between commits. It supports the detection of various common refactoring types from Fowler's catalog. Among the supported refactorings, all refactoring types detected by refactoring miner were considered in this study. Overall, our extraction process identifies in the 300 apps 13,500 commits with refactoring, 42,181 refactoring operations, and in total 271,263 commits. And we analyze a set of 10 metrics based on Schneider and Kummerer. And to calculate the values of these metrics, we use the common open source Secametrics tool, namely Secametrics, which is a command line based tool. And then to investigate whether or not each metric is improved by refactoring, we use two statistical analysis methods. The first one is the statistical significant analysis. By using the Wilkinson sum rank sum test to assess the statistical differences between the distribution before and after the application of refactoring, and the non-parametric effect cliff delta to compute the effect size. The second one is the causal inference analysis. By using the difference in difference model, which take into account two groups, the treatment group and the control group. So here we can see in action in animation an example of causal inference methods using the GID model showing the impact, the refactoring impact in quality metrics. So we can start with the data for the treatment and the control and its before and after the treatment, which is the refactoring. We can see what the average outcome was before and after the refactoring. In the treatment and the control groups, we take out the difference, and that is the difference in difference estimate of the refactoring effect. Coming on to the result where we address our research question. First, for each commit change of both groups, we compute its corresponding metric values before and after each commit in both treatment and control groups. So here we can see the general distribution of metric values before and after commit changes in the treatment and the control groups. Then we provide a detailed analysis for both treatment and control, where each column reports the impact of the respective refactoring types based on the difference in difference technique, the behavior indicated, whether the refactoring impact is positive or negative, and the p-value as well as the cliff delta. So let's start with coupling. We can see from the table that refactoring has a significant positive impact on coupling in terms of both the CPU and RFC metrics, while no significant impact was found on the NOZ metric. The most impactful refactoring that promote low coupling are move methods and extract and move methods. Moving now to cohesion, we can see that the LCOM, TCC, and LCC metrics tend to exhibit significant variation with attribute and method level moving to related refactorings, such as move attribute, move methods, and extract and move methods. However, as shown in the red color, some refactoring worsen the LCOM metric, which suggests Android developers to pay attention when dealing with cohesion. For complexity, We can see that several refactoring types tend to improve complexity by decreasing the WMC metric. The most impactful refactoring are extract superclass, extract method, and move method, which typically help simplifying method structure and reducing duplicate code. For the design size, we can see that most refactoring types tend to reduce the design size metric, which has the log and variables quantity. The most impactful refactorings are extract superclass, pull-up, push-down methods, and move methods, which typically help reducing duplicate code or moving code between classes, hence improving the design size. Finally, for the inheritance, we can see that the hierarchy level the refactorings tend to improve the inheritance quality attribute, such as pull-up attribute, extract superclass, and push-down methods. Looking now at the control group results, we can see that the different quality metrics did not exhibit any significant change with non-refactoring changes, except for the log and variable quantities metrics that tend to increase after each commit, which is normal since the design size related metrics increase over time as the project evolves. These results provide more evidence that the metric changes observed in the experiment data are due to refactoring activities and not to change. Moreover, it's worth noting that our findings in Android apps share some similarities with desktop apps for the majority of quality metrics. To sum up, we find that the vast majority of applied refactoring lead to positive impact on quality metrics, and the moving related refactoring operations are the most helpful in improving quality. The LCOM stood out as the least consistent metric, improving for some refactoring types and disimproving for others. Finally, we found that for the non-refactoring commits, most metrics exhibit significant change except the design size metric. So what to do now? There are some applications that come out in this paper. First is for researchers. So they need to further exploit quality metrics and refactoring in mobile software development. Second implications are for practitioners. So our results indicate that developers can apply refactoring operations that do not improve their app structure quality during refactoring, and in particular for the cohesion metric LCOM. While LCOM tend to be very volatile and refactoring, as also shown in prior works, these results indicate that there is a risk that developers degrade their app's structural quality while performing refactoring changes. So Android developers should be careful about their app's code quality. Also, there is a need for Android-specific refactoring tools. Finally, the implication for educators. So they need to learn refactoring best practices. To sum up, we present a study aimed at investigating the impact of refactoring on quality metrics in Android apps. We mined 300 open source apps containing 42,181 refactoring operations in total. We found that several refactoring types lead to positive impact on quality metrics. The outcome stood out as the least consistent metric, improving for some refactoring types and disimproving for others. We found also that for the non-refactoring commits, the metric exhibits no significant change other than the design size metrics. Note that our dataset is available in our replication package for future replication and extensions. As a future work, we plan to analyze other refactoring types and investigate their impact on internal and external quality attributes. We plan also to extend our study to more open source and commercial Android apps to better generalize our result. Also to develop Android-specific refactoring tools to better support developers during maintenance and evolution. As a summary to our presentation, first we show the motivation of our study. Second, we show the empirical setup, then the data collection, and finally, our results. So thank you for attending the presentation.